Section 6.8 is about complex numbers, and that is basically the expansion of the set of real numbers. So the complex numbers are a larger set of numbers than the real numbers, or another way of saying it is that the real numbers are a subset of the complex numbers. This section has several objectives. Number one, to express imaginary numbers as b times I, where b is a non-zero real number, and complex numbers such as a plus bi, where a and b are real numbers. We define I in just a moment. Then how do we do addition and subtraction with complex numbers and multiplication of complex numbers, and then writing expressions involving complex numbers, powers of I in the form of a plus bi. And then we find conjugates of complex numbers and divide complex numbers. And then last but not least, we'll determine whether a given complex numbers is a solution of an equation. First of all, let's define the complex number I. And so we define the number I to be the square root of -1. That is, I equals the square root of -1. And when we square both sides, then I squared equals -1. Which of course tells you right away that I is not a real number, and that's why it's called a complex number. So the key to it is to accept the definition of what I is. You don't have to wrap your head around it, but just accept it and work with it. That would be the most important thing right now. So here's a little bit of an explanation about imaginary and complex numbers. So it begins with the observation that we already knew, that negative numbers do not have square roots in the real number system. However, mathematicians have described a larger number system that contains the real number system and in which negative numbers do have square roots. And that system is called the complex number system. So we begin by defining a number that is the square root of -1, and we call this new number I, as we just did up here. And so here's how we do this. To express roots of negative numbers in terms of I, we can use the fact that in the complex number system, the square root of minus p is equal to the square root of -1 times p, which is equal to the square root of -1 times the square root of p, where p is a positive real number. So we begin with example number 1, the square root of -5. So we can write the square root of -5 as the square root of -1 times 5, and that we can write as the square root of -1 times the square root of 5. And since the square root of -1 equals I, that then becomes I times the square root of 5. And we can also write it as the square root of 5 times I. But we have to be careful that it doesn't look like the I is under the radical symbol. Okay, so just be careful that there's no confusion possible. It's safer to write this way, but this is more normal to write the number first and then the, like think of it as a variable, but of course it is not variable, but it has a letter. And so this would be more normal to write, but this is safer to write. Anyway, we can write it this way, or we can write it the other way. Similarly, when we go to number 2, we can look at the square root of -25, and we can write the square root of -25 as the square root of -1 times 25, or as the square root of -1 times the square root of 25. And the square root of -1, of course, is I, and the square root of 25 is 5, so it's I times 5, or 5i. So here's no confusion possible, so this would certainly be the preferred way of writing the result, but this is correct also. But this would be the preferred way of writing it, so 5i. In the guided solution, we are looking at the square root of minus 54, which is equal to minus 1 times 54. So it's equal to the square root of minus 1 times the square root of 54, which is equal to I times the square root of 9 times 6. Of course, the square root of 9 is 3, so we have I times 3 times the square root of 6, which is equal to 3I times the square root of 6, or 3 times the square root of 6 times I. Again, be careful that doesn't look like, well, that we know that the I is not part of the radicand. So here's the imaginary number definition. An imaginary number is a number that can be named bi, where b is some real number and b is not equal to 0. And then is the definition of a complex number, and that is a complex number is any number that can be written as a plus bi, where a and b are any real numbers, and that either one or b but not or both can be 0. So that then also includes the real numbers, for all those where b equals 0. Okay, so the next thing is some operations with complex numbers. And so first we're going to look at addition and subtraction, which is really quite simple, because the complex numbers follow the commutative and associative laws of addition. So we can add and subtract them as we do binomials with real number coefficients. That is, we collect like terms. So this will become apparent here very easily when we look at some examples. For instance, if we are to add or subtract these complex numbers, a plus 4i plus 8 minus 7i, what we need to do is we simply add the real parts, so we can write that as 7 plus 8. This is equal to 7 plus 8. That's from the real parts. And then plus 4i minus 7i. And 7 plus 8 is 15. And 4i minus 7i is minus 3i. So it's really quite simple and very intuitive. And number 7 works similarly. We combine the real parts, minus 5 minus 7, plus minus 6i plus 12i. So then for the real part we have minus 12, minus 5 minus 7, and then for the imaginary part, minus 6i plus 12i is 6i. So this then is the answer to number 7. Next, we're going to subtract two complex numbers. Again, we subtract the real part, 8 minus 5, so it's 8 minus 5, plus 3i minus 8i. So 8 minus 5 is 3, and 3i minus 8i is minus 5i. And number 9 is very similar. So here we have, we look at the real parts, and that's, for the first one, it's, of course, it's 5. And for the second complex number, it's minus minus 7, so it'd be plus 7. And then we have minus 4i plus minus 4i, and then minus 3i. So there would be 5 plus 7 is 12. And minus 4i minus 3i is minus 7i. So you can treat complex numbers almost like binomials. Now, when we multiply complex numbers, it's a little bit different. And so we need to treat each factor as a separate part. So we will write minus a square root of minus 25. Well, we know that that's equal to I times the square root of 25, or I times 5, or 5i, times, there would be I times the square root of 4, or 2i, or I times 2. And so we have 5 times 2 is 10. I squared, and we know from the original definition the square root of, well, I is equal to the square root of minus 1. When we square both sides, then I squared equals minus 1. So then we multiply 10 by minus 1, since I squared equals minus 1. So the answer then is minus 10. In other words, in this case, we don't multiply the radicands and say, well, minus 25 times minus 4 is equal to 100. So when we deal with negatives, or with square roots of negative numbers, that approach does not work. Similarly, for the next problem, number 11, we have square root of minus 2 is the square root of I times the square root of 2, and the square root of minus 17 is I times the square root of 17. So then we have I times I is I squared, and the square root of 2 times the square root of 17 is the square root of 34, and since I squared equals minus 1, this is equal to minus the square root of 34. For number 12, we can rewrite this as I times minus 6 times 7. So that's I squared times minus 42. But I squared is equal to minus 1. So minus 1 times minus 42 is equal to 42. You don't really have to take all the in-between steps. If you can skip some steps, that's fine. I just want to be very explicit about it. Here we use the distributive property, as we always have when we have parentheses, and we want to eliminate them. So minus 3i times 4 is simply minus 12i. And then we have minus 3i times minus 3i, so plus minus 3i times minus 3i. So that's equal to minus 12i. And minus 3i times minus 3i, 3 times minus 3 times minus 3 is plus 9. So plus 9i squared. But I squared is equal to minus 1. So we have minus 12i minus 9. Or to write it as a complex number, minus 9 minus 12i. And number 14 is very similar. We multiply 5i times minus 5. That's minus 25i. and 5i times 7i is equal to 35i squared. And since I squared is minus 1, this then becomes minus 35 minus 25i. So as you can see, the operations with complex numbers is fairly straightforward. The addition, subtraction, multiplication. Again, the important thing to keep in mind is to remember what I squared is, that I squared equals negative 1. So here's a guided solution, number 15. So here we have here multiplying two complex numbers. 1 plus 3i times 1 plus 5i. So 1 times 1 is 1 squared, or 1. And then 1 times 5i is 5i. And 3i times 1 is 3i. And 3i times 5i is 15i squared. Now we can combine like terms. So it's 5i plus 3i is 8i. And then I squared equals minus 1. So that gives us 15 times negative 1, because I squared equals minus 1. And so now we can combine the 1 and the minus 15, which would be minus 14 plus 8i. So that would be the answer to this problem here. So we have a few more of this type here. We multiply 3 minus 2i times 1 plus 4i. So 3 times 1 is 1. So it's equal, 3 times 1 is 3. And then 3 times 4i is 12i. And minus 2i times 1 is minus 2i. And minus 2i times 4i is minus 8i squared. So now we can combine like terms. So we have 3, and 12i minus 2i is 10i. And minus 8i squared, since I squared equals minus 1, minus 1 times minus 8 is plus 8. So that would be then 3 plus 8 is 11, plus 10i. 3 plus 8 equals 11. And number 17, we can use the expression a plus b quantity squared. So it'd be a squared, in this case 3 squared, plus 2 times 3 times 2i, plus 2i squared. So 3 squared, of course, is 9. And 2 times 3 is 6, times 2 is 12i. When we square 2i, we get 4i squared plus 4i squared. But I squared equals minus 1, so that becomes the negative 4. And 9 minus 4 is 5 plus 12i. So 4i squared is equal to minus 4. Before we solve the powers of I exercises here, let's think about a couple of things. Number one, we know that I squared equals negative 1. Number two, when we raise minus 1 to an even power, so n equals even, then the result is positive 1. And number 3, when we raise minus 1 to an odd power, m equals odd, then we get minus 1. So let's remember that. And the last one would be to remember that we raise a power to a power, and now it's a to the m, by multiplying a to the m times n, and vice versa. For example, we can write a to the 46th power as a to the second power to the 23rd power. Okay? And you see in a moment how we apply that. So keeping in mind what I just explained, we're going to rewrite I to the 47th as I to the 46th power times I. And now we're going to write I to the 46th as I to the second power raised to the 23rd power times I. The next step is that I squared equals minus 1, and we raise that to an odd power. So we know that that's equal to minus 1 times I, which is the same as minus I. So that's the answer, minus I, and that's the solution to number 18. So here the answer is minus I. So applying the similar thinking to number 19, I to the 68 we can write as I squared to the 34th power, 2 times 34 is 68. So now I squared, since that's equal to minus 1, and we are raising that to an even power, that is equal to 1. Similarly, I to the 85th power for number 20. So for number 20, we write that as I to the 84th power times I. And so that's the same as I squared to the 42nd power times I. And so that's equal to minus 1 to the 42nd power times I. So we are raising negative 1 to an even power. That's equal to 1. So it's 1 times I, and that's simply equal to I. So that's number 20. So the answer here is I. And number 21, we can write it as I squared to the 45th power. And since I is equal to minus 1, we're now raising minus 1 to an odd power of 45, so that's equal to minus 1. Let's do number 22. So that's 8 minus I to the second power raised to the second power times I. And so I squared equals minus 1. So it's equal to 8 times minus, and I squared is minus 1 raised to the second power times I. And since I squared raised to an even power is equal to positive 1, this becomes then 8 minus 1 times I, or simply 8 minus I. for number 23, we have 7 plus 4 times, we know I squared equals -1, so it'd be 7 minus 4 or 3. I to the 34th we can write as I squared to the 17th power, because 2 times 17 is 34, minus I to the 54th power, and 54 we can write as I squared to the 27th power times I. And so I squared is equal to -1, and -1 raised to an odd power is -1. And here we have a minus, and I squared is -1 raised to an odd power is equal to -1 times I. And so that means we have -1, and minus times a minus is a plus, so plus I. And here's a guided solution problem. So we have 6I to the 11th plus 7I to the 14th power. So we can write that as 6 times I to the 11th plus 7 times I to the 14th power. And so we can write that as 6 times I squared to the 5th power. It's to the 10th, I to the 10th plus I is I to the 11th, so that's correct. And so here we can write 14 as I squared to the 7th power. So now, since I squared equals -1, this becomes 6 times -1 to the 5th power. And then 7 times I squared equals -1 to the 7th power. And so -1 raised to an odd power is equal to -1. 6 times -1 times I. And again, here we have 7 times -1 raised to an odd power is equal to -1. So that means we have now -6I minus 7. 7 times -1 is -7. And so then we write it as -7 minus 6I. Since it's a complex number, this is the A part and this is the BI part. Next we're going to talk about conjugates again. We've talked about conjugates before for rationalizing denominators, but in the context of complex numbers. The conjugate of a complex number A plus BI is A minus BI. And the conjugate of A minus BI is A plus BI. So the conjugate of 6 plus 3I is 6 minus 3I. That is the conjugate. And the conjugate of -9 minus 5I is -9 plus 5I. And the conjugate of -1/4 I is plus 1/4 I, or simply 1/4 I. So when we multiply two complex numbers that are conjugates of each other, we use the property of A minus B times A plus B, which was A squared minus B squared. And similarly, when we had radical expressions of this type, the radical disappeared. And similarly, when we multiply conjugates, then the imaginary part disappears also. So here's how it works. So this is equal to 7 squared minus 2i squared, which of course is 49, minus, and 2i squared is 4i squared, but I squared is equal to minus 1, so we have 49 plus 4. Since I squared is minus 1 times minus 4 is positive 4, so the answer is 53. Similarly here, we have minus 3 minus I times the minus 3 plus I, so they are conjugates of each other. So it means we have minus 3 squared minus I squared. And minus 3 squared, of course, is 9. And minus, since I squared is equal to minus 1, we have minus minus 1. That's 9 plus 1, or 10. So now we are going to apply the principles of conjugates to simplifying the division problems here. So we multiply numerator and denominator by the conjugate of 1 minus 3i, which is equal to 1 plus 3i. Again, it's similar to rationalizing the denominator, 1 plus 3i. So we know in the denominator we get 1 squared minus 3i squared, so 1 squared minus 3i squared. And in the numerator we get 6 times 1 is 6, and 6 times 3i is 18i, plus 2i is 20i, and 2i times 3i is 6i squared, and since I squared is equal to minus 1, we get minus 6. So then in the numerator, 6 minus 6 is 0, we have 20i. And in the denominator, 1 minus, and then 3i squared would be 9i squared. And since I squared is minus 1, so minus 9i squared. This then becomes 20i divided by I squared is minus 1, and minus 1 times minus 9 is plus 9, and 1 plus 9 is 10. So that means this is equal to 2i. And when you look at the original problem, it's not obvious that that's equal to 2i. So the simplification like this makes it a lot simpler. For number 32, we are multiplying the numerator and denominator by the conjugate of minus 1 plus 4i, which is minus 1 minus 4i, minus 1 minus 4i. So then in the denominator, we get 1 squared minus 1 squared minus 4i squared. And in numerator, we get 2 times minus 1 is minus 2. And minus 8i minus 3i is minus 11i. And then we have 3 times minus 4 is minus 12i squared. So that means in the denominator we get 1, and then 4i squared is 16i squared. And since I squared is equal to minus 1, so minus 16 times minus 1. And in the numerator we get, so minus 12i squared. I squared is minus 1, and minus 1 times minus 12 is 12. So 12 minus 2 minus 11i. And And so that's equal to 10. And in the denominator, we have 1 minus 16, so it's 17. And then we have minus 11i divided by 17 also. Next, we look at the solutions of equations. And so the question is, the equation x squared plus 1 equals 0 has no real number solutions, but it has two non-real complex solutions. Determine whether minus I is a solution of x squared plus 1 equals 0. So when we replace x with minus I, we have minus I squared plus 1, is that equal to 0, question mark. But minus I times minus I is I squared. So we have I squared plus 1, is that equal to 0? Well, I squared equals minus 1 and plus 1, and that does equal 0, so the answer is yes. Minus I is the solution. Similarly, in the next exercise we asked, determine whether 1 minus I is a solution of x squared minus 2x plus 2 equals 0. So what we do here now is we replace x with 1 minus I. In the next exercise we asked whether 1 minus I is a solution of x squared minus 2x plus 2 equals 0. So it means we replace every x with the expression 1 minus I. So that means x squared means 1 minus I squared minus 2 times x, or 2 times 1 minus I plus 2. So the question is that equal to 0? So 1 minus I squared would be 1 squared, or 1 minus 2I plus I squared. And 2 times minus 2 times 1 is minus 2. And minus 2 times minus I is plus 2I. Plus 2, is that equal to 0? Well, 1 minus 2I, and I squared is negative 1, minus 2 plus 2I plus 2, is that equal to 0? Well, 1 minus 1 cancels out, and minus 2 plus 2 is 0, and minus 2I plus 2I is 0, and since 0 equals 0, the answer is yes. 1 minus I is a solution of the quadratic equation x squared minus 2x plus 2 equals 0. This concludes section 6.8 and also chapter 6.